Hi, everyone. Okay, this is the third part in our little series on cross product. We're almost done. The last thing we have left to do is prove that the magnitude of the vector given by the cross product equals the area of the base of the parallelepiped. Uh, that's kind of fun to show. We're going to do it in a different way. It's interesting. Then finally, a quick video about the equation of a plane, just to remind everybody, and then we'll be able to start on the projective plane and homogeneous coordinates.
We showed that the vector is normal to the base, but we still have to show that we still have to show that the magnitude of n equals the area of the parallelogram. So we have area. And we still have to show that the height, this is the normal vector. We still have to show that this equals the area. That area, we need to show that. Okay, so I'm going to show this in a much easier way, or a much more simple way that's very cool because it shows you how you can manipulate vectors. So the point is that we're in 3D space here. And we don't know where these two vectors are going to be. They can be anywhere. So A could go this many down, this many over, and this many up. And B might be up here, which goes this many down, this many over, and this many up. So these are arranged. The two vectors, we don't know how they're going to be in space. They could be anywhere. And at first blush, you might think this is really hard. How do we find the area between these two vectors without knowing what the orientation is? But the cool thing is you can change the bases. These two vectors are indeed floating around in space. What we can define where x and y are. We don't have to start with x and y here and then say a and b are in relation to them. We can just rearrange it so that x goes this way and y goes this way, and then z goes up from there. And that's what we're going to do. So we're going to use the bases as such that I goes along A, and that then B is in the same plane, perpendicular, and then Z comes out that way. So in that situation, so we're putting these two vectors in the xy plane with A along the x-axis. Okay, so in that case, A, then it has a component along x, so that's A1, no component along y because it's parallel with x, and no component up from there because it's on the x-axis. B, then, it has some measure along x, and then also a component along y, right? We can't just say that it can't just be 0, B2, because that would imply that it's parallel to the y-axis, but it's not necessarily. It could be anywhere between the x-axis and the y-axis. So it's going to have an x component and a y component, but still we made the xy plane so it's the same plane that those two lie on the xy plane, so that there's still 0 for the z component. Now, so given that, let's first of all just figure out what is the area of this parallelogram. So we have an A and a B, and they're in the xy plane. So we know that A is the base, and this is, well, we know that the height of this is just B2, right? Because it goes out B1, up B2. So the height is just B2. So the area of this, base times height, is A1 times B2. Okay, we know that that's the area of this parallelogram. So now what we need to do is look and see if that matches the cross product that we're looking at. So if we have I, J, K, oh, and then we have A1, 0, and 0, and then B1, B2, and 0. If we just take this, it's 0 minus 0 times I. Here we have 0 minus 0, J, and A1 B2 minus 0, K. So 0, 0, and A1. So it's vertical, it's coming out of the page, and it has a length of A1 B2, which is exactly what we wanted. That is the area. So that proves it. So the magnitude, so just to summarize one more time quickly, with the cross product, we're looking for the volume of the parallelepiped. A, B, C. And we're taking that with A cross product B equals the volume. And we've shown that since C is C1, C2, C3, then if we dot that with I, J, K, then we get C1, C2, C3, A1, A2, A3, B1, B2, B3. And we showed that indeed this is normal, and the magnitude of this is the area of the base. That's what we wanted to show. So we're all done. So again, all the cross product is, it's not a thing in, it's not a thing, it's just in order to make this equation work. It's really about the determinant, because it's really about the volume. And the way to make this work with C, by dotting with C, you need a vector perpendicular that has the area A. And that's what so if we do it this way, that's what we get. That's it. So that's the cross product, dot product, and determinant.
Okay, and that is it. Well, that finishes our little series on the cross product, and that finishes our little series on vector operations. We've shown the dot product, the determinant, and the cross product. We've justified all of them. We've given an intuitive understanding of all of them, so that finally, I think, we can comfortably remember where each one of them comes from and what they're doing. So one last little video. The next one is just reminding us of the equation of a plane. And then finally, we will look into the projective plane and homogeneous coordinates. Once we're done with that, we'll go back to the elliptic curve and complex coordinates, and then modular forms. And then we'll move on to Chapter 2, elliptic curves in detail. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. and click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.